The first three stopped. So when did the audio stop?
In the beginning.
At the beginning.
As soon as you went off screen, the
And
audio also went off. So keep yourself up. You don't have to keep Vladimir and me up, but you got to keep yourself up.
all right,
You, yeah, start with
is the
that
screen
conclusion.
up
And
now?
let's,
Can you see the
yeah, I can see and
screen?
I can hear. So let's start with that conclusion.
All right. All right. All right. I've already talked about all these slides. And so, anyway, after 40 years of the orthodoxy believing in the existence of dark matter and much money and time spent on theory and experimental identification, no such invisible dark matter has ever been detected. And it now seems that this idea is a chimera, an illusion or fabrication of the mind. So they need dark matter, basically. Mainstream needs dark matter in order for their theories to work correctly. And what does that really mean? So I'm going to go over here to inflation and dark matter. Okay, so inflation and dark matter are really basically related. Dark matter is needed to make inflation work. Okay. So you still hearing me?
Yes, sir.
Is everything good?
Yes.
All right. All right. So what is the motivation for bringing in dark matter into the picture? Well, we have the grand unified theories that come to fruition. The grand unified theories are the new advances in particle physics. So some books say that particle physics is sort of this, you have the discovery of the quarks, and then there's the business of the unification of the weak force with the discovery of the forget the W and the other particle. And so all these theories of particle physics, the standard theory of particle physics, all comes together and appears to be completed. And so by the mid 1970s, you have this theory of SU3, SU2, S by U1. I'm not going to go into what that means. The main progenitors of that, Glashow and Georgi, they have this new theory, the SU5 unification, that comes out in 1974. And so by the end of the 1970s, these grand unified theory ideas pretty much solidified, and they start moving into cosmology. They've pretty much solidified the particle physics theory. So now they want to move into cosmology. And this, shortly after this period, Guth proposes his inflation idea. And so a progenitor of the inflation idea is a standard model of particle physics is well established, but there's still problems. There's the magnetic monopole problem. There's the antimatter imbalance problem, because the theory is predicting a lot of antimatter is going to be produced in the Big Bang event. So that's a problem. Then there's the flatness problem, which is that the universe is sort of, in a sense, Euclidean. And in order for the flatness to be Euclidean, the cosmological theory is that the mass density has to be equal to 1. The known mass density is not 1, it's far less than 1. And so this brings on dark matter. The idea of the inflation is that that there is this very rapid period of expansion of the universe, very, very early on in the era of what they call the gut era, the grand unification theory. So there's an expansion that takes place before any atoms or are formed. I don't think even electrons or protons or neutrons or anything like that have been formed yet. And so this involves a negative pressure field similar in concept to dark energy, could drive cosmic inflation. So they need this energy field that causes the inflation. Inflation postulates that some repulsive force similar to dark energy resulted in an enormous and exponential expansion of the universe slightly after the Big Bang. Such expansion is an essential feature of most current models of the Big Bang. However, inflation must have occurred at a much higher negative energy density than the dark energy we observe today, and inflation is thought to have completely ended when the universe was just a fraction of a second old. Boy, that's a lot of stuff from Wikipedia. All right. And it's kind of confusing what's happening here because now we've got this dark energy mentioned in this, which kind of pushes the story forward. Okay, so inflation modifies the dynamics of the early universe. And so now we have a new model. So if you look at the cosmology books, they'll talk about the Big Bang model. Prior to 1980, they don't have these gut theory. The grand unification theories are not included. And the grand unification theory involves what's called symmetry breaking. And and there are different eras of symmetry breaking. And what I think this is an unfortunate terminology, but what it means is that in the beginning, there's only one force at the initial instant. There's only one force in existence. And then as the universe expands, other forces come into existence, the electromagnetic force. And then there's a separation with the stronger forces until after the expansion is complete, the existence of electrons and protons arises. And that brings on the theory, the previous theory of particle physics and the Big Bang theory. So essentially what the gut theory does is it gives an era that precedes the previous cosmological theories. But again, as I said, they needed, in order to bring this into the cosmological model that had existed previously, they had to bring in inflation, and then bringing in inflation means that you bring in dark matter. Okay, I'm gonna, and so inflation makes a definite prediction about the mass density parameter omega, and you can't have inflation if omega is less than 1. Since luminous matter gives values of omega much less than unity, dark matter is needed for inflation to be valid. Inflation can be correct only if dark matter exists. So you see here is and of course, the inflation theory says that the dark matter can't be baryonic, or protons and neutrons and normal matter, but non-baryonic. Baryonic, they mean normal matter. And dark matter must be distributed smoothly. Okay. And then there's the question of hot dark matter versus cold dark matter. And the modern theories, cold dark matter is required in the lambda CDM cosmology. So we need cold dark matter. So in order to make the galaxies, so the galaxies can condense, if the dark matter is hot, then the galaxies can't condense and stars can't form. That's my understanding of why the cold dark matter is needed. Okay. Main takeaway for the issue about dark matter and inflation is, if inflation is correct, then cold dark matter must exist. And it's required because in order to make their theories work, you got to have this cold dark matter It has to exist because it's part of the paradigm that has been created. Okay. Any evidence that dark matter doesn't exist cannot be used to justify a falsification of the orthodox standard model of cosmology. And what I'm saying there is, if you show that like galaxy rotation curves don't require dark matter, or you disprove that dark matter doesn't exist in galaxies to explain rotation curves, you can explain it some other way. That doesn't really get rid of dark matter. And the reason is because the dark matter idea is essential to the fundamental physics that they're using that underlies the theory of the gut theory and the inflation idea. Okay, so the dark matter is essential to those ideas. Okay. Does anybody have any questions about this so far? All right, you see do you see the dark energy problem here on the screen here? I changed is this working here?
I still see conclusion, the conclusion chart.
It didn't. Have not been changing?
No.
Well, nobody told me that I've been changing. Okay, so this is not working correctly.
But it looked like
so
you'd come
didn't tell me that when I was. So you didn't tell me that that the slides were changing, and I went through a whole new set of slides. Okay, that's confusing.
Yeah. That's because it was at the end of the slide, so I didn't know if you were going extemporaneous. While you're looking at that, let me make some general comment. The Big Bang Theory was in trouble from the beginning, and they had to invent inflation, which called for an expansion of the universe by a factor of 10 to the 35th or some huge number, unbelievable, in a small fraction,
Right.
1 over 10 to the 33rd, which, and no reason for it to start and no reason for it to end. That's what's been accepted for decades.
We have one of your slides on the screen.
So a dark energy problem. Do we have dark energy problem?
Yes.
Can you hear me?
Yes.
Yes.
Can you hear me?
Yes. Oops.
Does anybody hear me?
Yes, yes, yes. Can you hear us?
Thank you.
Yes, we are here.
All right. In a nutshell, the universe is 4% visible, 23% undetectable, and 73% unimaginable. Welcome to the cosmos, full of mass you can measure but not manhandle, given by a force you can infer but not explain. This comes from Tim Radford, who is I don't know if he currently is, but he was at the time the science editor for The Guardian, which is a famous British newspaper. And so I like this quote about the 73% unimaginable, 23%, and the 23% is the dark matter, and the 73% is unimaginable. So now we're up to the issue of during the 1980s, dark matter gets brought into the picture, And then in the late 1990s and the beginning of the new millennium, the idea that dark energy is needed, and that gets brought in and integrated to cosmology. Do you see this new slide here, dark energy, another ad hoc assumption?
Yes.
Yes.
Okay. This guy, David Merritt, identifies dark energy as an example of an auxiliary hypothesis, an ad hoc postulate that is added to a theory in response to observations that falsify it. And it's kind of, confusing there what he's saying. He argues that the dark energy hypothesis is a conventionalist hypothesis, that is a hypothesis that adds no empirical content and hence is unfalsifiable in the sense defined by Karl Popper. Okay, so talk a little bit more about that later. So we talked about dark matter that got brought in, justified by in Virginia Trimble's survey published in 1987. That was sort of an attempt to justify the existence of dark matter based on observations. But the real reason for bringing dark matter in and believing in it had more to do with the cosmological theory that was brought in by Gutt, and bringing in the latest particle physics theories. These people moved from particle physics. They'd solved all the problems in particle physics. Now they're going to solve the problems in cosmology. And so bringing that in brought in inflation, and bringing in inflation brings in dark matter in order to make the Gutt models work. Okay. So what is this dark energy? So they're saying 9 billion years after the universe began, its expansion started to speed up, driven by an unknown force that scientists have named dark energy. And of course, from this NASA site, they say, we don't know what dark energy is. Right now, dark energy is just the name that astronomers give to the mysterious something that is causing the universe to expand at an accelerated rate. Okay, so now we have another hypothetical. We had dark matter, which is a hypothetical substance, and now we have dark energy, which is a hypothetical energy. Yes. Okay, the term dark energy. Yeah. Okay. Back to where did this word come from? Okay, and like I talked earlier about where did dark matter, where did that word come from? This is a little bit different because there is this guy that we can pin it on who came up with this idea. So according to this gentleman, the term dark energy echoes Fritz Zwicky's dark matter from the 1930s and was coined by Michael S. Turner in a paper in 1998. So we can blame this guy, Michael Turner, for this word, for this terminology. And I think this terminology is very confusing and doesn't really help the issue at all. It's like dark matter. The term dark matter, what does that mean? I think it's really, in a way, designed to confuse people or make it seem more mysterious and exotic. And it's kind of a gee whiz kind of terminology that they brought into the picture. Okay, what's the reason for it? There were two projects in the 1990s to measure supernova. When they put these supernova onto the distance redshift relationship chart, and they found that it didn't agree with the cosmological models that they were expecting it to agree with, so they brought in dark energy. Now, says here, distance measurements to type 1 supernova indicate that the universe is accelerating and that 2/3 of the critical energy density exists in a dark energy component with negative pressure. This is kind of confusing to me. What they mean to say is that the rate of expansion is increasing with time. So the rate at which the universe is expanding is increasing. Okay. Here's a diagram that shows that. You start off with the Big Bang, which is this little teeny point at the bottom. Passage of time is moving upwards in this diagram, and it's basically just a two-dimensional diagram. So this diagram is showing what they call the expansion coefficient, the R factor. And the idea is that in the beginning, there's this initial inflation, and then there's kind of a coasting period where in the coasting period, maybe not sounding very technical, but anyway, this is the period when galaxies are forming. Okay, so the universe can't be, this initial inflation has to cease at some point, because if it continues expanding at a very rapid rate, the galaxies can't form, okay, because the matter is expanding faster than the gravity can cause the matter to condense into galaxies. So they have to slow down the expansion rate to allow galaxies to form. This is a crucial point. And then it's expanding again. So what you have is you have inflation, then kind of a coasting period, then re-expansion again. All right, this diagram shows the measurements of the supernova, and it looks like as you go further, the redshift is increasing to the right. It looks like that as you go further to the right, the distance is increasing faster. So the distance is above the line. So this is a kind of a simplistic diagram. Get off the internet that shows that without the dark energy, you get the dotted blue line. With the dark energy, the red lines, red dots represent measurements. And so then you do a curve fitting, and the curve fitting line that you get there, you use a formula and you fit it to the data. And so you get this line or function, and that function doesn't agree with the expected result. And so the argument is you need dark energy to explain the difference. Then there's this issue of the cosmological constant. And I've watched a number of videos on YouTube, and when they start talking about the cosmological constant, everything starts to get confused, and I can understand that, because in some places they say that dark energy is equivalent to the cosmological constant. Well, they don't really mean that, or they mean that it acts like the cosmological constant. May be a better way of talking about it. So dark energy acts like the cosmological constant, but it doesn't. The value of the cosmological constant, according to some people, can't explain the dark energy. So the value of the cosmological constant is too small to explain dark energy. So it's not, the dark energy is not the same thing as the cosmological constant. It's sort of similar to the cosmological constant in providing a repulsive force. And I think that's probably the best way to describe it. In some places, and I mentioned earlier, they talk about a negative pressure. When I first saw the negative pressure, this is part of what's confusing in the terminology. When they talk about negative pressure, I thought, what does that mean? I couldn't understand what was meant by negative pressure. So Actually, I think the term ought to be a repulsive force or a force that's opposite to gravity or an anti-gravity force. But they don't use those terms, and I think I'm not sure exactly why these terms aren't used. To me, I thought it was kind of confusing. Okay, I'm not really sure I want to talk about the de Sitter model right now, but the de Sitter model has, in a way, a universe that's continuously expanding exponentially from zero. And in this diagram, you can see it's the blue line. And the Sitter universe supposedly has zero mass. Okay, and so it's kind of rejected because it has zero mass. But it's an exponentially expanding universe, so it has a kind of dark energy-like characteristic in that the expansion is continually increasing. So in the de Sitter universe, the rate of expansion is continuously increasing, as opposed to the lambda CDM universe, which is the pink line, I think. Okay, and the lambda, it starts from zero. Now notice the de Sitter universe doesn't start at zero. It approaches t equals zero. It doesn't actually get to t equals zero because it's an exponential function, which I think is kind of an interesting advantage of the de Sitter universe. Anyway, the point I wanted to make here is that in the lambda CDM, which is the standard cosmology, there's the initial instant, then there's a rapid period of inflation, very rapid period of inflation. Then the rapid period of inflation slows down so galaxies can form. And then after galaxies have formed, it speeds up again. Okay, the rate of expansion speeds up again. So that's what this, I think it's a magenta looking line on my screen, kind of a pink or magenta line. And so that's what that's trying to show. So this, to me, is an important point I wanted to make. The Big Bang, I talked about this, the de Sitter model, there's no t equals zero, and it allows continuous creation. But there's no matter or radiation in the de Sitter universe, so they just get rid of that. Now, the other model that I've talked about and previously is which is also kind of interesting, is the Lemaitre model. And the Lemaitre model uses the cosmological constant, which is, I think, why that model is not how should I put it, not approved of by the orthodox. So in the Lemaitre model, you have a beginning, a t equals 0 point, and then it expands, and then it reaches a period of stability where supposedly the cosmological constant offsets the force of expansion. And so you get a period of during which the universe isn't expanding, and then it evolves into another period where the cosmological constant takes over and the universe starts expanding at an accelerating rate. Now, it's not real clear to me why why the lambda CDM model is better than the Lemaitre model, but I suspect it probably has something to do with the idea that the cosmological constant isn't strong enough to explain the measurements that they made in the lambda CDM model. So, okay. I'm going to. Okay. There's some different ideas about what causes the dark energy. There's the vacuum energy state. I'm trying to find that slide here. Oh, there's quintessence. Now, it's not really clear to me how these models, this quintessence idea, differs from the vacuum energy idea. Quintessence differs from the cosmological constant. Okay, so what we're talking about here is, according to what they're saying, the cosmological constant can't explain the dark energy effect. It's not, doesn't have the correct magnitude to explain it. As I understand it, it's too low. So there's not enough energy predicted by the cosmological constant to explain the observed dark energy effect. So they need to look for something else. So they have this idea of quintessence. Quintessence differs from the cosmological constant explanation in that it's dynamic. Okay, what do they mean by that? Well, it changes with time. So the cosmological constant is a fixed parameter that doesn't change, so it's not a function of time. But this quintessence model is that the effect of the quintessence, or the repulsive force, changes with the time parameter of the cosmological model. So the cosmological model has time, and time starts at t equals 0. Then it proceeds with a universal time parameter. Okay. And so what the quintessence model is saying is that the parameter that causes the dark energy is a function of time. And this allows them to explain why the dark energy force only becomes important after about 5 to 9 billion years. Then this is kind of confused. Quintessence can be either attractive or repulsive, so it can change its sign. That's interesting. Depending upon the ratio of kinetic and potential energy, that's kind of, it's kind of a flexible fudge factor. And the reason it's called quintessence is because it's proposed that this is a fifth fundamental force of nature in addition to the 4 fundamental forces of nature that have already been there. So this is a nice fudge factor, fix them up. Okay, vacuum energy. This goes back to the Lemaitre idea, and that Lemaitre used an unusual perfect fluid equation of state to interpret the cosmological constant as due to vacuum energy. So they're claiming that this idea can be traced back to Lemaitre. I talked about that earlier, because what you need is the force, this repulsive force that opposes gravity, has to change with time so that you get a rapid, in the case of the, you get a rapid inflation of the universe, then it slows down. That allows the galaxies to form. So you need a sort of a slow period. And then to fit the measurements, everything has to speed up again. Okay, and that's similar to the Lemaitre. That's basically similar to what the Lemaitre model says. And this fellow, now this apparently goes back to 1973. Tyron proposed the zero energy universe hypothesis, that the universe may be a large-scale quantum mechanical vacuum fluctuation where positive mass energy is balanced by negative gravitational potential energy. Boy, that's a big mouthful. And this is kind of a speculation, and I don't think it's become official. Okay, dark energy and inflation. Alan Guth proposed in 1980 that a negative pressure field similar in concept to dark energy would drive cosmic inflation. So what this means is that there's apparently an attempt to connect the dark energy back to the inflation theory and make the one idea explain both. Okay, so this is kind of my take on all this. Maybe it's confusing. The concept of dark energy adds complexity to an already complicated list of cosmological models. Okay, so there's a big mouthful there. You need to know a lot about cosmology. If you go to the history of cosmology, Einstein had a cosmology that was static. De Sitter came along in 1917, and this is pretty early on, and came up with his solution to the general relativity field equations. Then you have Friedman, and I'm not sure I was right about the same time as De Sitter, and he came up with solutions for the universe to the general relativity equations. Eddington, Arthur Eddington, was also involved in this and did a lot of work during this time. And he was a proponent of Lemaitre, who is this Belgian priest. And apparently, Lemaitre's ideas and work was kind of obscure and published in these obscure journals. And Eddington became his proponent. And sort of brought Lemaitre's work to the attention of the so there, and this is all work that was done before World War II. So there's a lot, and all these models and ideas are different. It's becoming very complicated. So on top of what perhaps we could call that era, the classical era of cosmology, these new ideas of inflation and dark matter and dark energy are being added on to these existing different models that have been developed. Now, these models have different parameters in them, and so they're complicated. What is the correct model? And so the idea was, starting in the 1960s and then continuing in the 70s, that they would be able to make astronomical observations that would be able to distinguish what the correct cosmological model is. But what we find out now is that this is a lot easier said than done. We've got a cosmological model, which they've accepted, called the Lambda CDM model, that has a lot of add-ons. It's got dark energy added into it. It's got dark matter into it. And then there's the issue of what role does the cosmological constant play, if any. So it's very complicated. So dark energy and dark matter really haven't done anything to simplify the situation. Okay, it looks to me like dark energy is an ad hoc substitution for cosmological constant needed to produce a variable repulsive force rather than a steady one. So the force has to change with time. If it's a fifth force, as in the quintessence. I think these are ad hoc fixes to the Big Bang cosmology rather than comprehensive mathematical solutions based upon a minimum of hypotheses. So thinking about it from my point of view, this is a big violation of Occam's razor. You just keep adding on these ad hoc fixes, and that's what we get from adding dark matter and dark energy into the picture. All right. Does anybody have any comments? Whoops. No comments.
Well, cosmology obviously is a very complex and difficult nut to crack, so I don't blame physics academia for not having come up with the right answer, but I do blame them for becoming so bound to a particular basic theory that they didn't use the scientific method, but when they found experimental data that went against their theory, rather than trying to rethink their theory, they just added fudge factor after fudge factor. And all of these fudge factors were actually dark fudge factors that had no basis in logic or in the empirical data.
Okay, do you see the screen here, persistent problems of Big Bang Lambda CDM cosmology?
Yes, see it.
All right. Okay, so this is kind of my, how should I say it, wrapping up. This is kind of a wrapping up of what I've learned, put it that way, what I've learned by looking into this stuff. And I can't say that I've looked into everything in tremendous amount of detail with a big microscope. So I could have missed something, but anyway, so I'm going to talk a little bit. This is what I'm calling persistent problems of Big Bang Lambda CDM cosmology, things that won't go away. Well, kind of the first one is violates first law of thermodynamics. Energy cannot be created or destroyed. So they got a theory that basically creates energy out of nothing, creates matter out of nothing. So looks to me like, and this is not my opinion, this is a criticism of cosmology and these models that comes from experts. That cosmology violates first law of thermodynamics. Energy cannot be created or destroyed. And the excuse is, I like to use the word excuse, the theory doesn't address before the beginning. So it doesn't address the issue of where the energy, what happened before the t=0 event. So essentially all they're doing is hypothesizing an initial condition. Okay. And then out of that initial condition, the entire universe evolves, but they don't justify how they got the initial condition. And I think that's kind of an excuse and an evasion. Some people think, oh, that's perfectly acceptable. I'm not sure I agree with that. Then this is another one. This one comes from Roger Penrose. He may not be the originator of it, but he certainly has talked about it. Violates the law of entropy, which requires systems under change to become less organized over time. So what he's saying, and I'm not really sure exactly I could state it, but if you're starting from the Big Bang, okay, that looks like this big, it's not an organized state of matter. It's a disorganized state of matter. It's, radiation and energy interacting and flying around in a big soup. And out of this soup of disorder, order has to emerge according to the standard ideas of physics and cosmology. And that would appear to violate the law of entropy that says that systems go from states of order to states of disorder. And he says that this is not evolving from disorder to order. And that's a violation of the law of entropy. And of course, there's an excuse that, well, this isn't really a correct description of the events, that the early universe is uniform and ordered and homogeneous, and it's not random and disordered. So that's the argument against saying that. So it's really not a disordered state. So the Big Bang really isn't a disordered state. It's an ordered state. And therefore, as the galaxies emerge from this dense ordered state, okay, and then galaxies emerge, then actually disorder is coming out of order. So there's a difference of opinion there. Okay. Now we're back to the whole idea of bringing in particle physics models with Gamow back in the 1940s was to explain the creation of the elements. And so the whole idea of bringing particle physics into cosmology was an attempt to explain where the elements come from. But the problem was soon discovered that the Big Bang, as originally envisioned by Gamow and Alper, his students, and there was the other student, Herman, and then, of course, Jim Peebles in Princeton sort of redeveloped this idea, that they discovered that they couldn't really create elements other than hydrogen, helium, and lithium and beryllium in very small quantities. So where do the other elements come from? Where do the other elements come from? And that's where more ad hoc hypotheses come in to play. Well, these other elements are created in stars. Okay, so there's nuclear fusion in the stars. So the hydrogen is created in the Big Bang. That becomes stars. The stars burn. That's the term they use. The stars burn as fuel, hydrogen, and then create other elements. And you have what's called the CNO cycle. But then it turns out you can't explain the heavier elements. You can only explain the elements being created to a certain point. And then you need to bring in another ad hoc assumption, which is that the other elements are created in supernova. Okay, that seems like an ad hoc. That's another ad hoc, bringing another ad hoc in to explain something that couldn't be explained by the standard approach. And then the supernova explosions spread out all these elements that have been created. So the star creates oxygen, carbon, silicon, these other elements. And then it can no longer, it runs out of its fuel, and then the star collapses. And in the process of collapsing, the star explodes and disintegrates its outer layers. And during this explosion, the heavier elements are created. Now, the problem is, how does all this gas, all this material that's being expelled in a disorderly fashion, because it's a big explosion, the supernova is a big explosion. So now we have a violation of the law of entropy, which means that somehow or another, the material that's been expelled in the supernova explosion condense back into stars. So it has to come back into stars, and then the process is repeated. And so this process looks to me like it violates this concept, the law of entropy. And of course, there's a big problem. I'm not convinced at all that stars condense from gas. Okay, then I talked a lot about this, that the inflation, that you need this repulsive phase. So in other words, there's an initial instant of creation, then you need an expansion phase, and then the expansion phase has to cease, and then you get a slowdown of the expansion. That slowdown of the expansion allows stars and galaxies to form, and then the rate of expansion has to speed up again. And all of this kind of is ad hoc in my mind, because you need to put kind of like a piecewise model together where we're going to use this phenomenon and yet this theory to explain the initial phase, and then we're going to have another theory to explain the phase where galaxies are being formed, and then we're going to have another theory that's going to explain the dark energy expansion phase. And this all seems ad hoc to me to sort of make a model that does all that. Okay. Then you have the problems of the star formation. This is a biggie here. What is the source of angular momentum? Angular momentum is a really big problem. As far as I know, these models don't really address the angular momentum problem. If you assume that the clouds from which stars are formed are rotating initially, it turns out you get too much angular momentum than is observed. And so that's a real problem. So they have to fiddle with the star formation models to get the angular momentum right. And there's all kinds of ad hoc fixes that come into play. The second one, how do galaxies form in an expanding universe? I've talked a lot about this. Fred Hoyle, I pointed this out, I think, a couple of weeks ago. Fred Hoyle didn't believe that galaxies could form from the Big Bang. He thought that this really, how can you have an expanding universe that's this cloud of gas, and the universe is expanding, and you have this hot gas that's the result of this Big Bang explosion? How is this going to condense to form galaxies? And that problem is still out there. It's never been satisfactorily solved, in my view. Why does the inflation stop so that the galaxies can begin? What's the reason for that? Why would inflation stop? Okay, they don't. I don't know. There's an explanation of that. Then there's the observational fact there are no population 3 stars. So you need, in order for their theory to work out correctly, you would need a first generation of stars that have the primeval elemental constituents. So they're made up of the primeval, and I don't mean the hot Big Bang part, but after the gas, the elements have been formed, the hydrogen and helium are formed, and presumably they're uniformly distributed in space. And then out of this hot cooling gas medium, the stars and galaxies will form. And so the stars that are created in this first generation are called population 3 metal poor stars, because there hasn't been enough time for the heavier elements to be synthesized and supernova explosions to create the heavier elements. But there are no population 3 metal stars that have been observed. Then there's, of course, this, I think this is interesting. How do supermassive black holes form in the early universe? Well, the observations, their explanation for quasars and very active galaxy nuclei is that they're supermassive black holes. Well, how can you have supermassive black holes when you've barely had time for stars to form? Okay, and they have to explode and eject gas, and that gas has to fall into black holes and in order to feed the black holes. And so this whole process of the black holes getting bigger and bigger by absorbing all this gas that falls into them from the stars that are doing supernova explosions, this takes a very long time. But it appears that they exist in the very earliest era of the universe at high redshift. So this is a problem. And then you have the issue of how do radioactive elements survive the long time frame? So if you have a supernova explosion, and all this gas gets ejected out into space, it takes a long time for that to condense together and form a star. Well, we know that, excuse me, that there are radioactive elements with half-lives. We can measure them, we can find them in the Earth. How is it possible for these elements to have survived long enough without decaying? Okay, so this is a problem. If the supernova explode, and then in that process create radioactive heavier elements, why haven't they all decayed by the time the solar system has formed? All right. All right. Now we're back to dark matter is required to produce critical density. So we need this critical density. It's not been detected in any experiments after 40 years. So 40 years, they've been doing these experiments, hoping to find some justification that dark matter is formed during the early phase or the gut phase of the Big Bang. And doing these experiments at CERN and different laboratories, I haven't found any evidence of any particle that would fit the requirements that they're looking for. Okay, so we don't have an identification of dark energy and dark matter. And we also have the problems with the violations of the first law of thermodynamics. I mentioned that earlier. What causes the dark energy to manifest itself only after 5 billion years? The dark energy doesn't do anything, it has no effect, and then suddenly it starts operating after 5 billion years. Okay. So here's kind of my point here. What I'm really driving at, this is kind of what my conclusion is about all this, is the Big Bang's not a theory. Okay, people talk about the Big Bang theory. The Big Bang theory is wrong. The Big Bang is not a theory. It's a scientific paradigm. It's a scientific paradigm. That means it's a set of ideas, beliefs, and I think beliefs is a better word. It's things that scientists believe that have to be true, okay, because that's their working, that's the basis for their research. So they have a paradigm, the scientific paradigm. It's the basis, the fundamental way that they're thinking about the universe. It's the fundamental way they're thinking about how stars and galaxies and planets form. And you really have to, how do you disprove a mindset? It's like a mindset. It's a belief system. It's more like a religion than science, okay? And that's the way these people are thinking. It's their framework in which they're doing science. It's their framework in which all their research is based on this framework. And so it's absolutely needed by them in order to proceed with their so-called scientific enterprise. Okay. Now, this paradigm, the whole point of it is it derives its power through the unification of classical physics, and I use that word advisedly, with quantum physics. Okay, so the classical physics is general relativity. Okay, although some people might argue that general relativity is not classical physics, but it's kind of based on the Newtonian laws of gravitation. It's a way of thinking. It's a classical way of thinking about gravitation, and then it's combining that with quantum physics. Okay, and bringing those two together. Okay, so the Big Bang cosmology is an amalgam of these scientific paradigms. So in a way, it's a combination of paradigms. You have the general relativity paradigm, the relativity idea. largely a paradigm. And then you have quantum mechanics and particle physics. That's another scientific paradigm, and they combined them together and created this super paradigm, if you will. Okay, and it's very difficult to challenge a super paradigm. That's kind of my point I'm getting at. Okay, so there are two observational pillars that support this super paradigm idea. It's the expanding universe hypothesis, and that brings in general relativity. And then the cosmic microwave background radiation, that supports the particle physics idea. And so when you have the cosmic microwave background radiation, that really, they really like that idea as supporting the necessity of having the grand unified theories, the particle physics ideas that they've become enamored with. And then that gets brought together with the general relativity that predicts an expanding universe, if we believe the models. And so those two ideas brought together, that's what modern cosmology is. And so the modern idea, the standard model we have, it's a mathematical theory that implements the Big Bang paradigm, but it needs these ad hoc add-ons in order to really make it work. Okay, so what are my final thoughts about this? Okay, in the end, we have free will to choose for ourselves what to believe. So I think as human beings and free-thinking scientists, we can choose for ourselves. We don't have to accept what the orthodoxy says. And I don't think that they have a compelling scientific consensus that forces us to believe in this ideology of the Big Bang paradigm. Okay, as I said, it's a paradigm. It's a cosmological framework for explaining where the stars and planets come from, how did the universe originate. It's their paradigm for believing that. The philosophical objections are significant, and I talked a little bit about that, that it's an ad hoc, that the fixes are ad hoc, that it's a conventionalist philosophy that says, well, you sort of have to accept this because we say so. And some of the quotes, one Alan Sandage quote, well, this is the best we have and you have to believe it, that sort of thing. So there's in a way, scientists are required to march in lockstep to this paradigm. Okay, and the way I see it is there are two ways we can approach this. As dissidents, we can either accept the conventionalism, or in other words, believe without really questioning what the official orthodox position is, or we can be skeptical. I choose to be skeptical. And my final conclusion is that not enough attention is being paid. They're not really giving any money to looking at different alternatives. And they're out there, but they're just largely being ignored. The scientific establishment, they're completely trapped in the paradigm of the Big Bang. That's their that's the good science way that they've chosen, and they're marching down this road. Okay. And they're not going to deviate from this road because that's the road they're on, and they want to stay on it as long as they can. That's where the money comes from. Okay. Here's my final little comment about this is I heard about this guy, Michael J. Disney. Some of you may have heard of Michael J. Disney. I didn't know about Michael J. Disney, but he's put out a paper which is critical of the whole cosmological establishment. And amazingly, it looks to me like he agrees with my viewpoint of it. The crux of today's cosmological paradigm is that in order to maintain a mathematically unified theory valid for the entire universe, we must accept that 95% of our cosmos is furnished completely by unknown elements and forces for which we have no empirical evidence whatsoever. For a scientist to be confident of this picture requires an exceptional faith in the power of mathematical unification. Okay, so in other words, he's saying you've got to be a believer in order to accept the cosmological models that the Orthodox has developed. An exceptional faith in the power of mathematical unification. Okay.
Thank you very much, Harry.
Thank you very much.
I agree with virtually everything that you say and with what Disney says. I might add 2 quick points before I yield to someone knowledgeable like Vladimir. Not only was there no evidence for the mainstream construct of dark matter, but when they looked for it, like in our solar system, the empirical evidence was that it was not there. So that was rather striking. In addition, the supposed empirical evidence for dark matter is that at the periphery of spiral galaxies, stars are moving at a velocity that's inconsistent unless you add in the concept of dark matter. But that was based on a simple error that most people, high school students, myself, able to see, is that they were using the formula that's consistent with a spherical galaxy, where the force of gravity will decrease by 1 over the r squared. Whereas if you use the formula correctly for a spiral galaxy, the velocities are what you'd expect from Newtonian gravity, based upon what the real matter that we know is there. The other thing, quickly, just to show that I don't automatically agree with every criticism of Big Bang Theory, is that, Harry, you mentioned arguments that it wasn't agreeing with the second law of thermodynamics, but Kent Mayhew has developed a new theory of thermodynamics that is simpler than the current one and is quite a bit more accurate in its predictions. The original thermodynamics was created by, the original ideas were created by looking at internal combustion engines and treating it as a closed system and not accounting for energy that escaped through the bounds of the internal combustion engine. But it turns out if you open up and have a closed system and not a purely statistical approach to theory, that you get a much simpler and actually superior theory of thermodynamics. So I don't go along with the violation of second law of thermodynamics as being a problem. So that's my point, except that the CNPS would like everyone to be a critical thinker rather than someone who is set in a set belief system and just twists everything to conform with their belief system.
Well, of course, in all of these issues, and this is kind of the point I was really kind of getting at, is you can look at these things as violations or falsifications of their paradigm, but they're not going to change their paradigm because they're completely committed to it. because
Right.
it's a belief system.
Right.
Okay. And the point I was really trying to get at is that according to them, you sort of have some magic. There needs to be some magic involved. That first there's this Big Bang explosion. Okay, so they justify the initial conditions by saying that's not really a subject of inquiry. They just assume the initial conditions. So there has to be some energy assumed at the beginning that then is converted into matter. And that, I'm not an expert on all this, but so they've assumed an initial condition, and then from that they apply this gut theory, grand unified theory, which has got this symmetry breaking events. Okay, the Higgs field is brought into play, and that separates out the forces. Okay, the weak forces separated, and then the strong forces separate, and they have these different symmetry breaking events. And these are, of course, in very short periods of time at the very beginning. And where does the energy come from that starts all this off? Well, that's not, it's magic. You have to just assume that it's true. And then, then they have their explanation follows from that. Okay, but the problem I have is that all seems to work out, but the problem, in my view, comes when you try to explain how that becomes the real world that we live in. Stars, planets, galaxies. How do those things evolve out of the Big Bang? They don't really have a really convincing explanation for that. That's really where the real problem is, in my opinion. All this talk about dark matter and dark energy and all that, that's all nice, for us to talk about and criticize, but they need those concepts in order to get to the point where galaxies are forming and to explain what they've observed. And I don't think they can create stars and planets and galaxies after they get to the point where they think they're going to come about, because it requires gas clouds to condense to form stars and planets and galaxies, and they can't, and none of that works out. That's, in my view, creating order out of disorder.
Vladimir?
That's one of the, well, I was going to say that's one of the reasons I like Vladimir's theory, because Vladimir's theory, I don't think, has that aspect to it. Vladimir's theory is that we start off with ordered, high states of condensed matter, and then those disintegrate to form stars and galaxies. So we're going from a highly ordered state to a less ordered state. So I think his theory gets around this entropy problem.
Thank you so much for good words about my model. But first of all, let me ask you a couple questions about this prevailing Big Bang model. First of all, if they suppose that expansion is a confirmation of the theory, let me ask you the question. Expansion, where is the center of expansion? Where is this initial singularity in our world? Do they know about it?
Right. Good question.
Expansion without center, it doesn't exist.
Well, this is one of those points of terminological confusion. If you go and they talk about the bugs on the balloon and that sort of thing. They're talking about expansion without a center, but it's certainly, I don't really like the idea that there's a T0. That's why I like the De Sitter's idea. De Sitter's model doesn't have a T equals 0. It never gets to T equals 0. They make a couple of assumptions. One of the assumptions is that there's a linear law. In other words, that time operates linearly, and they can extrapolate back in universal time to some point t equals 0. Okay. And that to me is questionable right on the face of it. The other one is what they proceed is the logic. If you go back and you read the earlier papers, the logic is we're going to run the clock backwards. Okay, so they run the time clock backwards. Since the universe is expanding, if you run the clock backwards, the universe has to shrink. Okay, at some point, according to them, the universe should shrink to 0 at some time. It's assuming that the model that you're using for the expansion of space is linear. Okay, and yes, if you have a linear model, it'll go back to 0 if you accept that model conditions. But there's also this other idea that there's a limit to how much you can shrink space. So in other words, they adopt the idea that there is a Planck limit, okay, that when you get, so they're using the physics of modern day nature of space and extrapolating back and then saying, well, the physical laws that govern the nature of space as they exist today are the same as they were during the Big Bang at t equals 0. And I don't really see how that follows. And that is because they're smashing together the particle physics ideas with the cosmological ideas. And I don't see that model fits together. The expansion of space, as Vladimir has pointed out, what does it mean? Does it mean, to me, if it's a mathematical dilation, okay, and I can keep shrinking space and space forever and ever and ever to infinity because there should be no limit, okay? That's the assumption in general relativity there, that it's a mathematical dilation or contraction, if you will. But that's not the assumption in particle physics. In particle physics, they assume there's an absolute limit to how small space can get.
But in any case, there is no center of expansion, no center, correct? Because they never showed experimentally with anything, with any experimental data shows where is this center of expansion. Because expansion, the word means you have your center, initial singularity, and then you have your expansion. It's obvious. This expansion idea works only if you suppose initial singularity at t0. T equals 0. What is important in my model, there is no t0. There is no such time 0. And what is important, even this linear law of time variation is not right. Because in my model, all the parameters, they depend on, inversely depends on a cosmological time. And if you will see cosmological time inversely proportional, then t0 means infinity, but there is no infinity. That's why I have a limitation in my model with tau about 10 to the minus 18 seconds, and then you don't have any problems with t0 problem. You see what I mean? Even the idea about solar system or some other linear law of time is wrong. Our fundamental parameters, they depend on time.
Well, I'm not disagreeing with that.
That's why, all this value is transaction to t0 going down. It's not right. It's not right. Okay, that's why there is no confirmation of this initial singularity in any case, with theory, without theory, but we must have at least one experimental data result, but we don't. The second point is microwave background radiation. The idea that each photon has a wavelength, and then during transfer of these photons through the space, this wavelength increase, It's absolutely wrong because the people, they don't know quantum physics too. Because in quantum physics, quantum object, they have only four momenta only. That's why they don't have wavelengths. Wavelengths is a classical notion that belongs to ensemble of photons. That's why they don't have this explanation, the right one for microwave radiation. And what is important, this is one of the most important confirmation of their model. Come on, both of them, they don't work for us. For me, it doesn't work at all. That's why, two main points. What are the pillars of this model? What is the experimental confirmation? It's wrong. It's absolutely wrong. Because even in microwave background radiation, they put some ad hoc idea. Each photon have a wavelength. It's wrong. That's why, and confirmation based on this wrong idea. I'm very sorry. I can talk about the disadvantages of this model too much. It's not the task of our talk about with you today.
Don't be sorry. What we need is alternative views that make sense.
Yes, yes, I'm trying to do for 24 years this making sense.
Oh, I forgot to mention.
But nobody wants I'm sorry. Harry, you wanted to tell something.
I forgot to mention. Well, I explained that. I forgot to mention that this guy did this paper, and I forget the date of it. Was 2014. I forget exactly when, but anyway, they published a paper where they said there's no gravitational lensing in the CMB measurements. Okay, and when I heard about this, I thought, what? How can this be? I mean, their idea is that there's gravitational lensing in these clusters, but it doesn't show up in this cosmic microwave background. And what these guys are arguing is that, well, that means that the cosmic microwave background may be a local phenomenon because we can't confirm it at a distance because we don't see any gravitational lensing effect. And that apparently hasn't really gone anywhere. I don't think they want disconfirming evidence.
I'm sorry. Let me continue. It's a very good point. My microwave background radiation, it's a local phenomenon. You know why? Because there is so named evil axis of evil that, there is a correlation between properties of this microwave background radiation and the ecliptics of our galaxy. You see, at the very beginning, Big Bang knew about where will be our solar system, our galaxy, and what will be the direction of this galaxy, ecliptic, and all this stuff. It's unbelievable how you can explain this axis of evil without interaction of this microwave background radiation with matter, because black body radiation can be only when you have your thermal equilibrium with some matter. It's not photons separately moving inside of the vacuum without any interaction. It doesn't mean black body. Black body, by definition, it's a thermodynamic equilibrium with matter. Outside or inside should be some interaction. That's why even evil of axis of evil, it's part of the interaction of this microwave background radiation with plasma around our solar. It doesn't matter. It's another story. Maybe some days I will talk about this axis of evil, that it's against this idea of microwave background radiation generated at 380,000 years after Big Bang. It's absolutely wrong.
Yeah, others have given empirical evidence to back up what Vladimir is saying, like Robitaille and some others.
There are no experimental evidences of Big Bang model. It's ad hoc, all of it. And what is important, there is no even logic. If you have your logic, you must put some hypothesis and then develop this logic. There is no logic in the Big Bang model at all. I don't know how to take it. It's a religion. You're absolutely right. It's not a science.
What would the cosmic microwave background look like if there were gravitational lensing? I'm assuming that the the Milky Way center would be the thing that would be doing the gravitational lensing. But the general question is that I have is, what would it look like if there were gravitational lensing?
It should be some fluctuations in microwave background radiation. Now there are about 1 microkelvin. It's a 10 to the minus 6 out of the value of this temperature. And if it could be this lens, it should be much more pronounced fluctuations of it. That's it, simple like this. But there is none.
So lack of variability is your point. Would there also, if there were gravitational lensing,
let me answer Jim's question.
focusing of energy
My
on a
understanding
particular
is
point?
that the gravity.
Go ahead, Ari.
My understanding is that this should cause. My understanding is that this should cause cool spots in the microwave background radiation because it spreads out the light from the cosmic microwave background, and it has to do with the fact that the gravitational lensing reduces the surface brightness, if you can understand how that works. But that's the argument behind it. So they look for cool spots that would be correlated with galaxy clusters, and they don't find any. That's my understanding of it. But again, this is, something that was done many years ago that kind of basically nobody's paid any attention to as far as I could see. And I thought it was kind of interesting because either gravitational lensing is wrong or something else is wrong. It doesn't quite, they don't add up, is the point.
Well, I thought perhaps I'm missing something quite basic, but I thought gravitational lensing in the CMB might produce hot spots.
Do you have any other comments there, Jim?
Mhm.
Well, just that I thought that the
I'm going to add.
I thought that the gravitational lensing, if it occurred in the CMB, might create hot spots, just like a magnifying glass held out in the sun would create a hot spot where the light focused.
But you cannot arrange hot spot without cold spots. You see, it is redistribution of energy in any case. That's why Harry is absolutely right. If there is some hot spot, it will be some cold spots too. Variations in this fluctuation will be much more pronounced than it is right now. Sorry.
We only got 10 minutes.
Maybe Cornelius wants to ask some questions, here right now in our green room.
Well, that's my understanding of it.
I don't really have too many questions. I mean, I think even speculating on what the Big Bang was is kind of, more of a waste of time than anything. I'm more interested in, where the universe is currently.
Okay. Is there any other comments here? I did want to kind of finish up, if there are not. Cornelius, do you have any comments you want to make?
Am I cut off?
I don't see anybody else in the green room.
My microphone mustn't be working. I'm talking about.
Is he talking? Oh, he's muted.
Yeah. Okay.
Sorry.
Harry, I think you've become asynchronous with us.
Who?
By the way, let me just mention that what Harry has said and the others have said have sparked some skepticism about Big Bang theory, etc. You should look at our previous talks by Vladimir that talks about an alternative to the Big Bang theory, that addresses and overcomes all of the problems with the Big Bang. It's a totally different view, and it doesn't seem to have these fundamental problems that the Big Bang theory has.
Thank you so much for these kind words, Nick.
I take it my
Well-
mic isn't working. Is that right? My mic's not working?
Yes.
We can hear you, but I think Harry is behind us or in time.
Okay, all right. Well, my comments are, like I said, I'm not so much interested in the Big Bang because I think it's a lot of speculation when you go back that far, and deciding whether where it was or wasn't a beginning is not really my interest. My interest is more, why are they looking at dark energy and dark matter? I don't believe that they exist as particles, as they're saying. I believe there's energy there, but it's not necessarily in a particulate format. And I don't see, the redshift in the universe, to me clearly shows that there's a distance increasing between us and distant objects. It may or may not be because those objects are moving away. It could also be because the space in between us and them is increasing in distance. It's like you driving on a flat road, and all of a sudden, you come back the next day, and somebody dug a big valley between the same 2 points, so you have a longer distance to travel. And so I see it as like when the universe when the gases come together, create objects, and the objects come together and create galaxies, and that you have an extremely large, massive gravity well between us and far distant objects. And that gravity well is just going to be like that large dip in the road getting between you and them. Is going to make the distant object, as the gravity wells grow, is going to make the distant objects appear to be farther away. But in a straight line, if you're not following light, then you have the object being the same distance away. It's just on the other side of the valley that light has to travel through. Those are my comments.
Okay.
As far as speculating on the Big Bang, the rest of the conversation to me was just in one ear and out the other. So I don't care to just spend my time doing that.
Yeah.
Okay, thank
Well,
you.
I think we've lost Harry.
Looks like it. Well, Rick, I guess you get to close the meeting.
James, do you have anything else? Oh, here's Harry. Maybe he's Harry?
Your final
I
word.
turned it off because my computer is getting overloaded.
Mm.
All right, I'm going to remove I'm going to sum it up here. We're getting towards the end.
Good.
I'm trying to figure out how to remove people.
Or we can remove ourselves.
All
That
right.
might help you.
Summarize your presentation today.
All right.
Please.
Well, Cornelius raised the issue. He doesn't. The whole point of this, and I tried to make that pretty clear at the end. The discussion is really kind of about freedom of choice in science, and Michael Disney talks about this. If you go on the internet, you get some of his. Apparently, he created a controversy around 2000, and I hadn't heard of this guy until very recently, and he sort of has a criticism of the way science is being done. His criticism of cosmology is that it's very conventionalist, and you have to adhere to the orthodox view. And what happens from this is that all of the physical ideas that are out there explaining how the Earth arose and stars and galaxies, they all have to adhere to the, astronomy, physics. They all have to adhere to a paradigm, and that paradigm is fixed in the cosmological model that has been adopted, just like the standard model of particle physics is become fixed in orthodoxy. They've also fixed the standard model of cosmology. That's also fixed in orthodoxy. And Disney's argument would be, that science has marched down this very rigid path of options, and now the options of what you can talk about in science have become very limited and constricted by the orthodoxy that they're imposing. And their orthodoxy that they're imposing isn't really based on really good science. I'm paraphrasing Disney's argument. And his argument would be something more along the lines of what I was trying to say in my summary about free will and belief. As scientists, we should have more free will to believe, what we want to believe, and not be and have what is correct science or accepted science to be an orthodoxy that everybody has to march to. And I think that's his point. He says that's strangling science. I kind of tend to agree with that view, that you can't propose a theory unless that theory is consistent with the orthodox viewpoint, and that orthodox viewpoint is now fixed in concrete in the cosmological Big Bang paradigm, which is also attached to the standard particle physics paradigm. And so to challenge Big Bang cosmology means that you're in essence challenging all of everything that is known in physics. And because to object to the Big Bang is to object to everything that they believe to be true in physics. All right, I'm going to end it here. We got a couple of minutes to go, but I don't really have much more. Do you have anything to add, Vladimir? Or I don't see Nick on here. Nick seems to have disappeared.
Let me tell you, you gave very good presentation. The feelings of anybody who will see your presentation will be totally negative against this existing Big Bang model. You showed the history of ideas. You showed the history of all these inventions, I mean theoretical inventions without any experimental proof. And then it's not convincing anybody, not only professional guys like you, like myself, some other guys, Nick, who knows something about cosmology, but the normal, regular people, including students and some other guys. That's why the value of your presentation, very big one, to show how Big Bang model right now in crisis. No doubts about it. Thank you so much. It was good presentation, as usual.
Well, thank you. All right, we're coming up on the end here. If you want to, anybody else has any comments or want to get in here? I want to sort of end this on, I noticed that I hadn't heard much about Disney, and I noticed that they don't really, basically on Wikipedia, they don't really talk much about him, but apparently he got forced out of his university job, which I thought was kind of interesting. I mean, we can't have any criticism of the way the establishment is doing things. And I think really what he was proposing is he wanted new ideas in cosmology. He was advocating for new ideas in cosmology, and I don't think that was really received very well. And I think that's what we're doing here, basically, is new ideas, and So I'm going to try to shift gears and not criticize the Big Bang so much as maybe look at other ideas. But you kind of need a background in cosmology, and you need a kind of a background in what is currently thought to be true in order to basically speak the language and understand the background of any new ideas. And that's what I've tried to do, is I've tried to clarify what the background is and where the ideas that are currently accepted come from, and hopefully accomplish that in the cosmology discussions on Sunday. Okay, we're going to have cosmology discussions tomorrow at 10, and there'll be a time shift because of the shift to standard time. If anybody out there would like to participate that isn't already on the mailing list, you can send me a message at kc3mx@yahoo.com, Harry Ricker at kc3mx@yahoo.com, and I'll send you an invitation. Okay, thanks everybody for coming by.
Bye.